All right, so let's start off here. These are these four reactions that we have from this chapter in addition to our electrophilic aromatic substitution reactions. All right, and these four are important because they convert ortho-para directors to meta-directors or vice versa, right? So we've already done an electrophilic aromatic substitution reaction. We put something on our ring. This is how we can change the identity of what's on our ring, okay? So this first one here, we're effectively chopping off this carbonyl group, are fully reducing that carbon. Our transition metals are often playing the roles of catalysts in oxidation reduction reactions. So that's what our zinc is doing here. And this reaction will, again, effectively chop off the carbonyl group, converting this acylation reaction into an alkyl group. All right? Now, this is important because, again, this changes the identity of what is on the ring here. We went from having this moderate meta-director, and this alkyl group would be considered what? Ortho-para or meta-directing? This one would be ortho-para. It's actually a weak ortho-para. All right, so this is one reaction where we can change what's on our ring here. Okay, we can also, you see we're also using zinc here in a reduction reaction. We're reducing this nitrogen, replacing its oxygens with hydrogens. And our nitro group we know is a strong meta-director. But what would aniline be? All right, to be clear, this is one of those ones that we have a special name for with the NH2 on there. That's aniline. With its lone pair located right next door to that ring, this one is a strong ortho-para director. All right, so again, using this reaction here, we're changing the identity of what is on our ring. One of the reactions that we learned about in the previous chapter was this oxidation reaction at that benzylic position. So converting this alkyl group into a carboxylic acid group. We said our alkyl group was a weak ortho-para. And what about benzoic acid? Another one we got a fancy name for here. What would that carboxylic acid group on benzoic acid do? Ortho-para or meta-directing? This is our example of this electron withdrawing group. All right, this is a moderate meta-director. All right, and our last reaction at that benzylic position was using NBS to perform this benzylic bromination. If we just pour in a ton of NBS, we'll fully brominate that carbon. And this again, starting out with this alkyl group, was weak ortho-para. And now we have this fully brominated carbon here, or a strong meta-directing group. All right, so these four reactions, we need to round out our set of reactions here. You should kind of have them in one little place, one little category in your brain, because again, these are reactions that convert ortho-para to meta-directors or vice versa. Okay, two reduction reactions here using zinc, an oxidation reaction using our sodium dichromate, and this bromination reaction using that excess NBS. All right, so we got two kind of things that we want to be able to do with regard to these electrophilic aromatic substitution reactions. All right, the first is what I call follow your reactions. Right, this is where I'm going to give you that benzene starting substrate. And I'm going to give you a series of reactions. And you need to be able to follow what happens to that benzene throughout the course of this synthesis. All right, so first, let's perform this nitric acid, sulfuric acid business. Then we're going to move on to fuming sulfuric acid. And then we're going to do a bromination. Okay? And what we're going to do is we're just going to simply follow what happens at each one of these steps here. So in order to get what my product is, we want to think first what happens after that first step. What am I left with? All right, what do we put on that ring with nitric acid and sulfuric acid? A nitro group. All right, now we're going to go on and do a second step here. So that nitro group is going to be on that ring, right? And more importantly, that nitro group is going to direct that incoming substituent to a specific point. All right, so first of all, importantly, let's identify what this reaction does. We said the first reaction put a nitro group on there. What does my second reaction do? Yeah, it's called a sulfonic acid group, that SO3H. That's what that's going to put on that ring. All right, and the question is, where does that sulfonic acid group go? So what I got to do is I got to look at what's already on the ring here, and I got to ask myself, is this an ortho-para or a meta-director? Our nitro group falls into which bucket? This is our meta-director, which means that it's going to want to direct to one of these two positions here, right? It's not that sulfonic acid group that gets to choose where to go. It's the nitro group, what's already on the ring, that's going to direct incoming substituents to a proper location. Now in this case here, no matter which one I choose, I would get the same molecule. So I'm going to pick this one right here. Boom. All right. But now I went on and I did yet another reaction. So now I'm going to start with what I just put on the ring. Now let's look at this reaction. Let's figure out what it is that we're attaching to our ring here. Br2 and aluminum bromide, what's that going to put on? A bromine. All right, so we know what we're going to put on there. The question is where? All right, so what we got to do is we got to say, we know our nitro group we said was a meta-director. So it wants to put the incoming substituent in the position that is meta to that nitro group, which would be right here. All right, what is that sulfonic acid group? Ortho-para or meta-directing? This one's also meta. So where does that sulfonic acid group want the bromine to go? To the position that is meta to the sulfonic acid, or this position right here. So in this case, both of these guys are in agreement. We want that carbon, that new incoming bromine to go to the same carbon, and that's where we would stick that bromine. Right? That position is meta to both the nitro group and the sulfonic acid group. So great, they're both going to direct that incoming substituent to that position there. All right, so then our final product here would just be this one molecule. Okay, so at each step we identified what it is that we were doing in that step, and then we had to look at what was happening, what was already on the ring, to determine where that new substituent will go. All right, so let's do another one. Again, following our electrophilic aromatic substitution reaction. All right, I want you all to try. I will tell you that you are going to now get more than one product for this particular reaction. All right, so keeping track of each step is going to be really important. right, what's that first reaction going to put on our ring? Bromine. So let's put that on there. All right, now we're going to do our second reaction. We saw this in the previous example as well. This will be a nitro group, a nitration reaction. All right, but we got to look and see where that nitro group is going to go by asking ourselves, what is bromine, ortho-para or meta-directing? So bromine is ortho-para. So it wants to direct that incoming nitro group either to one of these ortho positions or to the para position. Depending on which one I choose, I would get a different product. So I'm going to have to draw both a nitro group on the ortho position and a nitro group on the para position. All right, so then to do step 3 here, now I'm going to have to start with my two products. Start with my ortho. And my para. All right, this third step is going to attach what to the ring? A chlorine. All right, but again, the question is where? So let's look at this first example here, this first molecule. Bromine, we said, was ortho-para-directing, right? So that means that bromine wants to direct to the position that is ortho or para to the bromine. But what about that nitro group? Nitro group is meta-directing, right? So that means we need to look at the meta positions. That's where that nitro group wants that incoming substituent to go. All right, so again, they're both in agreement. They are both going to direct that incoming chlorine to the same position, same two positions. Now, which one I choose is going to give me a different product. So when chlorine is directed over here, this would be one product. All right, but I would get a different product. It's not symmetric if I added it over here. All right, so I'm going to do both my, let me just shrink this down. Okay, so I got to attach it to each position. All right, now there was this molecule also floating around here. So I again got to look. We said bromine was ortho-para. Only these two ortho positions are open. Nitro, we said, was meta-directing. Okay. Now in this case, either one of these that I choose, this molecule is symmetric as is, so no matter which one, I'd get the same product. So I only have to include the one. All right, but we would get a mixture of all three of these at the end here. And what we did is we just broke it up into each step and followed where our directors were going to be placing that substituent. Okay, let's do another one here. All right, so now we're going to take those same reactions here, but we're going to throw in this extra step in the middle These are one of our 4 reactions that we covered at the beginning of class, which is going to convert our ortho, para, and meta directors. Okay, so see if you can't follow these steps. All right, so importantly, those first 2 steps are the same. All right, so that very first step puts a bromine on the ring. The second step is that nitration reaction, putting a nitro group on the ring. Since bromine is an ortho-para director, we get one product where it's on the ortho position and another where it's in the para position. All right, now these reactions here, my zinc HCl, importantly, this is not going to put anything new on the ring. It's going to convert that nitro group into an amine. All right, so after steps 3 and 4, I'm going to lump those together. Now instead of having NO2 on the ring, now we have NH2 on our ring. All right. Cool. So let me get rid of this. Our last reaction here is that chlorination reaction, putting a chlorine on the ring. But again, I got to figure out where it goes. So I'm going to look. Bromine is what? Ortho-para or meta-directing? Ortho-para. So bromine wants to put this incoming chlorine either on its ortho position or its para position. All right, but what is an amine with its lone pair right next to the ring? Also ortho-para. So it wants to direct to the positions that are ortho and para to the amine, to that nitrogen. All right, so now we got a conflict here. Okay, so this is where we got to worry not just about ortho-para and meta-directing, but about the strength of those groups, right? Bromine was a weak ortho-para director, whereas that amine was a strong ortho-para director. So who's going to win? The strong, all right? So the strong is going to win. It's going to be the amine that dictates where that incoming group goes. So we're going to put one chlorine in that ortho position and another one in the para position, but specifically to that amine nitrogen. Let's see if I can move this over. Get you out of the way. All right, so previously, in our previous examples, everybody was in agreement, so there wasn't any sort of a conflict that we had to worry about. In this case, we do have a conflict, and so the strong is going to win. All right, so then given that same logic, everybody take a second, draw me my last product here, performing that third step on this molecule. All right, so the pair position's blocked up, so bromine wants to direct it to its ortho position. The amine wants to direct it to its ortho position, and again, who's going to win? The amine. All right, the strong will get its way here. Okay, so at the end, we're going to get a mixture of all three of these here. Cool. So this is all about following these steps here, right? I give you a list of reactions in a specific order. You're following those reactions in that order to determine what the product is going to be, all right? The other thing that I can ask you is instead to predict that pathway where instead of giving you the middle part, I give you the beginning and the end. Right? So how do we get from benzene to a particular product? All right, so let's start out with kind of an easier one here. All right, so importantly, you don't have to have your reagents memorized. You will be given a bank of reagents on the exams. So we have our 3 electrophilic aromatic substitution ones. I'm sorry, 6. All right, so these are our 6 electrophilic aromatic substitution reactions, plus we got those 4 that we just talked about earlier today that will convert from one to another. All right, so here's our reactions here, and you're going to choose which reactions and in what order we need to get from A to B here, to get from our benzene to our product, this guy here. All right, so everybody take a second, see if you can't reason through that, and then we'll walk through it. All right, so the first thing we need to do is identify what reactions we're going to need to use here. To put this bromine on the ring, I'm going to use my bromination reaction. Let's actually go A. Okay. What about my SO3H? Which reaction am I going to choose for that one? A through J, which one? D, so that would be my fuming sulfuric acid. Cool. So now I just need to figure out what order in which to carry out these two reactions. All right. What I want to do is I want to look at my product here, and I want to say, all right, these two are located meta to one another. So that means the first thing on my ring better be a meta director. All right. If I go through and I categorize, my bromine is orthopara, and my sulfonic acid group is a meta director. So which one am I going to do first? A or D? D. So I'm going to need to first do that fuming sulfuric acid. And then I can do my bromination reaction. Whoops. All right, let's do another one here. Again, we're going to try to predict our pathway. All right, A through J, how am I going to put a chlorine on the ring? B. And what about a nitro group? How am I going to put that on the ring? C. So now the question is, what order do I carry these two out? Well, if I look at my product here, these are para to one another. My nitro group is a meta director. My chloro group is an orthopara director. So which one am I going to do first? Yeah, that meta directing chlorination, orthopara directing chlorination reaction, followed by my nitration reaction. Okay, so this is now where you're given, you have a bank of reagents here, but you got to tell me which ones and in what order we need to carry out a particular reaction to synthesize a desired product. All right, let's make it a little bit more difficult here. All right, so let me show you what I think is the common trap that people are going to fall into here, and then we'll try to reason our way through it, all right? I think a lot of people can identify pretty easily what we need to put the bromine on the ring. That'd be this one here. For this alkyl group, this ethyl group, we can use that Friedel-Crafts alkylation reaction, okay? Now, if we look, what are these two groups in our product? What are they to one another? Ortho, para, meta. So they're meta to one another. And if we looked at bromine, we'd say, all right, bromine's an ortho-para director, but an alkyl group is also an ortho-para director. All right, so neither one of these are going to direct them, the incoming substituent, to a meta position. So how do I do this here? All right, they're clearly meta to one another in my product. I got these two ortho-para directors. This is how we know we're going to have to use one of those four reactions that we discussed at the beginning, right? One of these four reactions that would convert an ortho-para to a meta director, all right? And in particular, the one that would make an alkyl group is to actually first start out with that acyl group and then reduce it using zinc, HCl, and heat, all right? So I could use that green reaction there, E, to make an alkyl group, but that's not going to help me make my product. So instead, I'm going to use the acylation reaction in combination with the reduction reaction in order to get that alkyl group on there, all right? So now let's think about the order in which these occur. Am I going to do my orange reaction first? No, that would put an ortho-para director on there, all right? So the first thing I'm going to do is that reaction F. We can even say we know what R is. All right, and just to draw it out so we're super clear about what's going on here, after that first step, I will have stuck an acyl group on that ring. All right, and this is again helpful because that acyl group is meta directing. So it will direct that incoming bromine to that proper position, that meta position. So I don't want to reduce it yet. I need to next do my bromination reaction. Directing that bromine to that proper position. And then I can perform that reduction leading to my final product. All right, so we had this product that had two ortho-para directors, but they were sitting meta to one another, which is how we knew we had to use one of our four reactions here to convert ortho-para to meta directors. All right, or vice versa. Cool. All right, let's do one more here. so in some ways this one's a little bit more straightforward in figuring out what reactions we need, but the order is still going to be really important here. So my chlorine, I'm going to do reaction B, my chlorination reaction. There's really only one way we know how to put an amine group on that ring, and that's to first start out with a nitro group and then reduce it with zinc and HCl and sodium hydroxide. All right, so these are these reactions that we're going to need, but now we got to think about our order. Okay, chlorine is an ortho-para director. All right, but my amine is also an ortho-para director, and these are sitting meta to one another in my structure. Right, so again, I know I'm going to need to use, and I've already identified which one of these reactions here to flip the behavior of that group. All right, so then which reaction are we going to carry out first? We got to carry out that nitration reaction first. If we did our bromination reaction, that would put an ortho-para director on the ring. All right, so just to be clear, we can map out what happens at each step here. Okay. Am I going to perform reaction G now to reduce that nitro group? No, because that would turn it into an ortho-para director, and I need to put my next group on meta. So next, I'm going to do my chlorination reaction. Right? That ensures that that incoming group will be directed to the meta position. And now, in order to get to my product, now I can do that zinc, HCl, and AOH business. Cool. All right, let's just do one more here. All right, so step one, let's figure out what reactions we're going to need to use here. The sulfonic acid group, what one, A through J? That would be the fuming H2SO4, a bromine, reaction A. All right, what about this thing right here, though? A fully brominated carbon. All right, we're going to need to use our excess NBS, our benzylic bromination reaction. All right, but we need to put a carbon on that ring to begin with, so we'll also have to use that Friedel-Crafts alkylation reaction. All right, so now the question is, what order am I going to be doing these? You know, to some extent, you can kind of guess and check. If you can see the pathway already from the jump, great. If not, pick one to start with and just see if that works out for you, right? In this case here, we're going to need to know, we got a lot going on here. Okay, these are meta to one another. These are ortho to one another. And these guys are para to one another. Okay, so if we tried to start out with that bromination reaction, we'd be able to get this guy into the proper position here because it's ortho to the bromine, but we wouldn't be able to put anything meta to that bromine, right? So we can't start out there. Likewise, this thing down here is a meta director, and it doesn't have anything sitting meta to it, so I'm not going to start with that one. I'm going to have to first start with our alkylation reaction, right? So I'm going to, and I guess I can identify what that alkyl group is. It's just a methyl group. Okay, so after my first step, I'll have this alkyl group. All right. What do I want to do next? I'm going to want to do my sulfuric acid. I'm going to want to stick that sulfonic acid group para to that methyl group. And I would get a mixture of products here, but we're sort of assuming that we've got some purification, some sort of chromatography or something that's separating these out. All right, so yes, I'll have a mixture of both, but the only one I really care about is the one where it's in the para position. Okay, so this alkyl group we said was ortho-para. Let's just make note. So now, if we look at our two reactions here, rather our two substituents on the ring, one's an ortho-para director, so it wants to direct to those orange positions. The other one is a meta director, so it wants to direct to these meta positions. All right, let's note that's not where my bromine is in my final product here. All right, so we're going to have to now change the characteristic of that alkyl group by using that excess NBS. Now that goes from being this ortho-para director to a meta director. All right, I'm just going to say CBr3. All right, and not only is it a meta director, but it is a strong meta director compared to my sulfonic acid group, which is just a moderate meta director. So the sulfonic acid group still wants it to go to these purple carbons here, but now my strong meta director is going to win and direct that bromine to that green position there. Cool. All right, so we can either follow these reactions. If I put any of these reactions in a specific order, you should be able to give me the product or products of that sequence of reactions. but also we'll have this reaction bank here, and we need to pick the proper reactions to get the pathway from beginning to end, from substrate to product here.